Hey everybody, today is the day that we are going to get into stoichiometry. And let me tell you a thing or two about stoichiometry. It can get kind of hairy. That's not to say that it's not mm, unbearable. It's something that when you put it into the kind of right terminology or like a familiar terminology, you get it and you know it. So that's one of the kind of I would say the hangups that lots of people have about understanding and processing questions about stoichiometry. So today's going to be kind of an introduction to it. Wednesday is going to be a deeper dive into it. And we're also going to get into some new stuff on Wednesday. Now, with all of that said, what we're covering today, well, quite a bit of it is kind of a review. Um, because basically what we're doing is we're taking old tools and we're kind of associating them with something new. Now, stoichiometry, it's balancing chemical reactions kind of like on steroids. Um, so when it comes to balancing a chemical reaction or chemical equation, the nuts and bolts of it are whatever you've got on the left-hand side. And actually, let me go ahead and erase that. Whatever you've got on the left-hand side, you've got to have on the right-hand side. So your reactants on the left-hand side and your products on the right-hand side. You got to get those two things in sync with one another. So here, what we've got, we're going to look at our products. Actually, I'm going to go ahead and erase these right here. We've got carbon reacting with O2. O2 is one of your diatomic gases, oxygen, and that's going to produce CO. Now, immediately you recognize there's a little bit of an imbalance there. And so the first thing that you're going to do is you're going to balance just by kind of simplicity, you're going to balance the oxygens first. So now you've got 2CO. So that CO is a lot like this right here. You've got a Milky Way and a Kit Kat coming together to make one molecule. On your reactant side, you've got two independent carbons reacting with O2 to form those two CO molecules. Well, the only way that you get this to work is by throwing that 2 coefficient in front of the carbon. So this is a nice model for balancing chemical reactions. Um, but as you can imagine, there's a little bit more to it, and it might get a little bit complicated. One other thing that we did that will be useful as a kind of chemical reaction balancer of sorts is we played around with this tool. This was a reaction between N2 and H2. Both diatomic gases, nitrogen gas and hydrogen gas, react to form NH3. Well, how does that happen? Well, the only way that this is possibly going to happen, because we can look at our two components. We've got N2, that's one thing right here, reacting with one thing of H2 to form this right here. Well, what we determined was when we threw a 3 in front of this, 3H2, well, then we could throw a 2 in front of this. And lo and behold, our hydrogens are balanced. Because we've got 6 hydrogens here, we've got 6 hydrogens here. Now what that leaves behind is our nitrogens. Are our nitrogens balanced? Well, we've got a 2 coefficient, which the coefficient you can change. The subscript or anything like that, you can never change. You got N, 2 nitrogens there, and then you've got N2. So that's actually balanced. So for this question, when this equation is balanced, what's the coefficient for H2? Well, the coefficient for H2 is C. Great. Now, next up, we talked about the mole. We talked about relationships between moles. Now, 1 mole of something, just like we talked about a dozen something. If I had a dozen pens, that would have a certain mass. If I had a dozen, let's go with 20-pound kettlebells. If I have a dozen 20-pound kettlebells, we know that that's going to weigh 240 pounds because there's 12 in a dozen. Each one of them weighs 20 pounds, so that's 240. If I have a dozen pens, is that going to weigh 240 pounds? No, it's not. I thought about it for a while. I considered my options, and no, it's not. Now, what is the same? If I have a dozen pens and a dozen 20-pound kettlebells, I've got 12 pens and I've got 12 kettlebells. But the individual components are different from one another. Now, the relationship here, this Avogadro's number is 6.02 times 10 to the 23rd. And this is kind of like what I just did was a dozen, 12 here, and things. My example was pens, and I'm just going to label it KBs, 20-pound KB. Um, those two things, well, I can have a dozen of them, but then I got to know the mass of each individual component or each individual. 20, let me change that. 12 20-pound kettlebells. It's going to be 240 lbs. 12 pens. If I had to guess, 12 pens might weigh, I'm going to call it 0.9 lbs. Less than a pound is what I would bet. So when we talk about a substance and we talk about, H2SO4, well, we can figure out if you have 1 mole of H2SO4, that means you've got 6.02 times 10 to the 23rd of H2SO4. But what's the mass of 1 mole of H2SO4? Well, in order to figure out that mass, you've got to get the mass of, from the periodic table, hydrogen. I'm going to put in parentheses 2. The parentheses being how many of them. Sulfur, I'm going to put 1. And then oxygen, I'm going to put in parentheses and I'm going to say 4. Now, I think that sulfur's 32. I'm going to go ahead and take a minute to tab over, pull this up on the periodic table, but I believe it's 32 grams per mole. Yeah, it is. Okay, so this would be 2, this would be 32, and then this 16 is the molar mass of oxygen, so 4 times 16 is 64. So the molar mass of H2SO4 is going to be 2 plus 32 plus 64. Well, 2 plus 32 is 34, plus 64 is going to be 96 grams. So if you have 1 mole of H2SO4, it's going to have a mass of 96 grams. If you have 0.75 moles of H2SO4, it's not going to be 96 because 0.75 is less than 1. 1 mole of H2SO4 is 96 grams. 0.75 grams is going to be a little bit less. You could maybe even argue that it's going to be 25% less. Now, we're going to be looking at converting moles to mass and mass to moles. So that's basically what I just did back there. Here, what we've got is grams of sugars. Now, more than likely, the sugar in both of these is fructose. And fructose has a specific, formula. You have 25 grams of total sugars in fructose and then 45 grams of total sugars in your Skittles. Now, sorry for yawning, converting those masses to moles, well, let me go ahead and pull up I'm going to operate under the idea that these both have a mass or both have a sugar of fructose. Fructose is, why did it do that? So fructose has a molar mass of 180.1 grams per mole. So what I want to do right here is convert these into moles. So fructose is 180.16 grams per mole. Now, what I want to do is I want to figure out how many moles of fructose is in Twix. Well, what I'm going to do right here is I'm going to take this number right here, this 180.16 over moles, grams per mole, and I'm going to give myself and kind of rephrase it as a definition. Anytime you see 180.16 G divided by mole, that's the same thing as 180.16 grams per 1 mole. The 1 is not there, but it's kind of implied. So 180.16 grams per 1 mole. So I'm going to rephrase this. And I'm going to say 1 mole fructose is equal to 180.16 grams of fructose. Okay, it's the same thing. I just rephrased it. I presented it slightly differently. Now, we talked about and worked with dimensional analysis a little bit previously. Now, what I'm going to do is I'm going to take my masses of fructose, or what I'm imagining is fructose, this 25 grams, and I'm going to write that first, 25 grams. I'm writing that first because that's the amount that I want to convert to moles. Then I've got this statement right here that I just put together. That statement right there is kind of the conversion factor. Now, what I want to do is I want to multiply grams by, well, grams per mole. Okay. Now, another way that I can put that, and what I really want to do, I'm going to erase this multiply sign, and instead I'm going to put it in my dimensional analysis. Some people like to say this is the picket fence. Now, what I want to do whenever I'm setting this up is I want to put the units, or I want to cancel units out. What units do I want to end with for my calculation? And the question is, what am I trying to solve for? Well, I'm trying to convert, or I'm trying to solve for the number of moles of fructose. So I want to end with moles up top. So what that means is I'm going to write 1 mole fructose, and then on bottom, I'm going to write 180.16 grams of fructose. Okay. So I've got 25 grams up top. And what I didn't write there, but what is kind of implied, is fructose. 25 grams of fructose is the amount of sugar from my Twix. So I'm just going to draw a line up here. That's where it's coming from. So I'm going to say 25 times 1. So I'm multiplying across the top and then dividing by what's on the bottom. So 25 times 1 is, that's right, 25. Now, what I'm going to do is I'm going to say 25 divided by 180.16. And for that, I'm going to get 0.139. I rounded it, 0.139 moles fructose. Okay. So there's my moles of fructose in a Twix bar. Now, anytime I do a calculation like this, I always like to try to reflect on the answer and say, does that make any sense? And whenever I do, I think, okay, well, if I had 180 grams, I would have one mole of fructose. Now, in my Twix bar, did I have 180 grams? Or did I have less than 180 grams? Or did I have more than 180 grams? I had 25 grams, which 25 is less than 180. So since I had less than 180, and 180 is the amount to get me 1 mole, I have less than 1 mole, okay? So my answer should be less than 1. Now my question for you is 0.139 less than 1? Absolutely. So that gives me a little bit of, even if I kind of get stressed out, reflecting on and trying to redo my work, I look at that number and I think, okay, I'm in a good spot. Now, next up, I'm going to do the same thing for Skittles. I'm going to do it in the lower right-hand corner because I kind of used up all my other space, but the structure and the setup is the same. I'm going to provide a little bit more information. I'm going to write 45 grams of fructose. Now, in case you're looking at this and you're thinking, where did the fructose come from? The fructose came from kind of an assumption. And that assumption is that, well, candy and most like sweetened drinks like a Dr. Pepper or Coca-Cola is probably sweetened by high fructose corn syrup. Fructose is just one sugar. There's tons and tons of different sugars, but chances are it's fructose that was used for this candy. So that's where that's coming from. So I'm just saying total sugars and then putting parentheses, fructose. Okay, then what I'm going to do is I'm going to go back to my reference point, which is 180.16 grams of fructose is 1 mole of fructose. And like I said previously, I want to get grams of fructose on the bottom, so in the denominator. And the 45 is what I know and what I kind of want to get rid of. Now I need my conversion factor, which my conversion factor is 180.16 grams of fructose on bottom and 1 mole fructose up top. So now what I'm going to do is, well, before I go ahead and plug this into my calculator, I'm going to think 45 grams of fructose. If I have 180, and change the units if you want. Change the units to something that's a little bit easier for you to kind of visualize. But just be kind of cautious and remember, okay, I changed the units for my calculation. Let's just say $180. 180 fructose dollars is 1 mole of fructose dollars. Okay? How many fructose dollars does Skittles have? 45. Is 45 fructose dollars less than 180 fructose dollars? Yes, it is. So now I've got an expectation that I'm going to have less than 1 mole of fructose. Okay, if the dollars thing didn't work and 180 and 45 works for you, grams, perfect. Now what I'm going to do is I'm going to type 45, multiply that by 1, it's 45. Now I'm going to divide that by, and just so you're watching along at home, I did not press times 1. I just know that 45 times 1 is 45. So I can say 45 divided by 180.16. And I get that number right there. And I'm going to round that up and I'm going to say 0.250 moles of fructose. So I've got 0.25 moles of fructose in a bag of Skittles compared to 0.139 moles of fructose in a Twix. Now, you might, if you're kind of looking at that and trying to study it, well, just for, scratching an itch and kind of closing a book in your mind, well, these Twix bars amount to 250 calories and Skittles, whoa, 250 calories also. But the Skittles have so much more sugar. Well, the big difference is that Twix also have fat. And comparatively, Skittles don't have very much fat. But anywho, this is all important. Making these conversions is essential so that you can do any sort of chemical reaction. For example, here what we have is a mole and mass relationship in a chemical equation. One carbon atom, a single carbon atom, reacts with 1 molecule of O2. And that produces 1 carbon dioxide molecule. Boy, howdy, that's just great. And you know what? We kind of saw that previously. 1C reacts with O2 to produce CO2. Well, yeah, if you want to talk about a single carbon atom doing it and one single oxygen molecule doing that, yeah, great. This, just in case you were playing along at home, because I had to kind of do a mental uh, refresher here. This was our previous reaction. C plus O2 yields CO. This new reaction is C plus O2 yields CO2. So there is a difference between the two. Now, with that in mind, this all scales. Okay. So one carbon atom, well, that has a mass of what are known as 12 atomic mass units. One oxygen atom has a mass of 32 atomic mass units, and those two will come together to make carbon dioxide, a single carbon dioxide molecule with a mass of 44 atomic mass units. 12 plus 32 is 44. Well, for this question, is oxygen conserved, or what is conserved? Yes or no? Well, the number of atoms are conserved. Are the number of molecules conserved? No, they're not. The number of moles conserved. Well, 1 mole plus 1 mole, that would be 2 moles. So that's not conserved, but the total mass is also conserved. Now, just as we have that ratio, we could phrase this slightly differently. 1 mole of carbon atoms reacts with 1 mole of oxygen atoms, or molecules, sorry, to produce 1 mole of carbon dioxide molecules. That's true. So when you think about it at the atomic level, one atom reacts with one molecule to produce one molecule. Well, 1 mole of carbon atoms, 1 mole of oxygen molecules produces 1 mole of carbon dioxide molecules. Let me get rid of that. Carbon dioxide molecules. There we go. So the atomic level and the number of molecules react to produce, well, this many molecules. Now, another way to look at that is to look at Avogadro's number. Well, 1 mole of carbon atoms is 6.02 times 10 to the 23rd carbon atoms. 1 mole of oxygen molecules is 6.02 times 10 to the 23rd oxygen molecules. And that produces 6.02 times 10 to the 23rd carbon dioxide molecules. 12 grams, which is the same as 1 mole of carbon atoms, 12 grams of carbon atoms can react with 32 grams of oxygen to produce 44 grams of carbon dioxide. So I think that it's helpful to think about this relationship and this right here. There are some small differences between these terms. One carbon atom and 1 mole of carbon atoms. Slight differences, but important differences. Because when you're talking about one carbon atom, you're just talking about a single thought, a single thing. I always kind of think of like a ping pong ball. Whereas whenever you're talking about a mole of carbon atoms, you're talking about 6.02 times 10 to the 23rd carbon atom or ping pong balls. If it's easier for you, write out 602 and then 21 more zeros. If that's easier for you, just to kind of like wrap your mind around it a little bit better, do it. And I'm going to stop right there. I'm not going to write all 21 zeros out there. I got close, but I didn't get all the way. Now, in addition to all that, there are molar-molar relationships in chemical equations. And this is kind of the key of stoichiometry. This right here is a balanced chemical reaction. And this tells us that C3H8, that's a compound known as propane. And if you've ever watched the TV show King of the Hill, well, then you know that Hank Hill loves propane and propane accessories. Propane, C3H8. 1 molecule of propane will react with 5 molecules of O2. And it will produce 3 molecules of CO2 and 4 molecules of H2O. Now, in that process, or sorry, that process is very like, I don't know if I'd say tightly conserved or controlled. How would I exactly say it? It's a perfect ratio. It's a perfect balance. And with that, I want to ask you this question. What if you had 12 C3H8s? So we've got this propane. And let's say that we had 12 molecules of propane. How many would that, or how many O2 molecules would that react with? We've got this perfect ratio of 1 to 5. Well, before we get to 12, let's make an adjustment and let's bring it to, let's double that. What do you think that's going to do to the O2 or the O2 demand? Well, then we're going to need 10. Now, how much will that make? 10 O2. Well, then we're going to double the CO2, so that's going to get us 6 CO2. And then 8 H2O. So everything's going to scale up accordingly. So if we had 12 propane molecules, then we're going to have 12 times as many O2 molecules, which would be 60. 36 CO2 and 48 H2O. It all scales accordingly. So that's a mole to mole relationship and mole to mole ratio. Anytime you see this balanced chemical reaction, think about that as like the perfect ratio, the perfect kind of combinations. Um, and that perfect ratio can kind of be a guide for you. Now, whenever we have grams, it's a little bit different. Well, if we have 100 grams of propane, what mass of water is formed? Well, to answer that question, what we need to be able to do is go from effectively grams of propane to moles of propane, which when we have moles of propane, then we can go to moles of O2 and H2O, and then we can go to mass. So 100 grams of propane, let's say prop, we need to know the molar mass of propane. And I've got a periodic table up on another window, so I'm just going to pull that up. And that's going to get me, well, that would give me the molar mass of 44 grams is 1 mole. Okay. So 100 divided by 44 is, I'm going to call it 2.3 moles of propane. So what does that mean for the number of moles of CO2? Well, that would mean that we're going to get 6.9 moles CO2, and then 2.3 times 4 is going to be my moles of H2O. So that'll be 9.1 H2O. Okay, but now how do we get mass of H2O and mass of CO2? Well, we got to take this and say 1 mole of CO2. Look at the periodic table and determine that the mass of CO2 is 12 for carbon, and then 16 for oxygen, 16 for oxygen. So that would also happen to be 44 grams of CO2. Now for H2O, 1 mole H2O is, well, that would be 18 grams of H2O. So if we reacted 100 grams of propane, we would get, let's see, 6.9 times 44. And that's going to be 303.6 grams of CO2. And then 9.1 times 18 is going to be 163.8 grams of H2O. Now, it's very fair to look at those numbers and think, wait a minute, wait a minute, wait a minute. That mass isn't conserved. Where did this other mass come from? Well, remember, the other reactant here is O2. We're adding oxygen to each one of these compounds. Each one of these products has oxygen in addition to the carbon and hydrogen that are present. So the total mass would be conserved. It's just a matter of, well, these new compounds have other components to them. Now, in summary, this is what's taking place on that previous slide. We use the mass of propane to get the number of moles of propane. So we got that 2.3. Then we looked at our ratio from our balanced chemical reaction. Well, what is the perfect ratio of propane to CO2 and H2O? That would get us our moles H2O and moles CO2. And from there, we can use that to determine the mass of H2O and CO2, or the grams of H2O and CO2. Now, that's stoichiometry in a nutshell. Is this challenging? Yes. Is this something that you're gonna that everyone picks up after doing one practice problem? No, not at all. Now, there's a couple of resources that I would recommend using to help out understand this sort of thing. And one of them is, I'm going to add it to the page here, the web to our it's to the video. It is webqc.org slash balance dot php. It's a helpful page where you can kind of play around with, well, you make up a chemical reaction and say if I reacted 12 grams of this with 50 grams of this, or 12 grams of this, how much am I going to get? Now, with that said, we'll be revisiting this again in our next lecture, but for the time being, I hope this is helpful and I hope you have a good one. See ya.